Let's say I have a little ball above the ground on Earth. Now suppose that the mass of this ball is 0.5 kilogram. I know how I can find the weight of this ball. I can find the weight by multiplying the mass by g, the acceleration due to gravity. And the acceleration due to gravity, g, is normally given as 9.81 meters per second squared. So if I now calculate the weights using the formula mass times g, I'll get 0.5 times 9.81, and the answer will be 5, less than 5, maybe 0.4, about 0.49. Oh no, about 4.9 of a Newton. So we understand this. We know how to do this. What I like to do now is to go back to look at this idea of g. If you look at these units, we understand g to be the acceleration of free fall, meaning that every second, if I drop the ball would increase in velocity downwards by 9.81 meters per second. But there is another way to think about g. There's another way to do it. If you look at this formula, look at what we've done here. We have taken the g and multiplied it by the mass to give the weight, right, the force of gravity. So what this means is that if I have a 1 kilogram mass, okay, then g times 1 kilogram is just 9.81. If I have a 2 kilogram mass, I'll multiply 2 by 9.81. 3 kilogram mass, 3 times 9.81. So this means that I can also think about the 9.81. I can think about 9.81 as the force on every kilogram of the mass. So this is how it will look like if I rearrange this. If I rearrange this equation, if I divide both sides by m, I'll get g is equal to weight, which is the force of gravity, divided by the mass. So if I have a number of kilogram, then the weight, the force of gravity on the object divided by the number of kilograms is also equal to g. So this gives me another way to think about g. I can think about g actually as the force per unit mass. So this is a slightly more abstract way to describe it. So let's be a little bit more specific for this particular example. The force here is that we're talking about is the weight, or the force of gravity. Force of gravity per unit mass. So this we have seen this per unit way of describing a quantity before. So for example, per unit mass can be per kilogram, it can be per gram, if you like, even per per ton or per pound, whatever. Okay, so we can also think about g in this way. Now, in this way, this gives us another way to write the units of g as well. We know that g, the numerical value of g in SI units, is 9.81. Okay, so 9.81. But this time, if I think of it as a is weight, the force per unit mass. We know the unit of force is Newton. We know the SI unit for mass is kilogram. So therefore the force per unit mass in SI units must naturally be Newton per kilogram. So therefore we have another meaning of G now, or if you like, another way to think about G, another physical interpretation of G, as in the force per unit mass. So whereas when we looked at the acceleration, look at G as an acceleration, we called it acceleration due to gravity. So if we look at G as a force per unit mass, then there is a proper name for this way of looking at it, and the name is, let me write it up there, and the proper name is called the field strength. So field strength means the force per unit mass in a field where we have gravitational forces, and the idea also extends to other types of forces like magnetic forces, electric forces, but we'll talk about that another time. So for now, we think of this word field strength. All right, we have a new term called field strength, and the meaning of the field strength is simply the force per unit mass. And the field, of course, if you recall, field just refers to a region of space, can be around the ground or can be somewhere in outer space around the Earth. The field strength means the force per unit mass, and if I have a number like 9.81 with newtons per meter, which is called the field strength, it just means that I can use it to find the force by multiplying by the mass of the object. So that's how we can use a field strength. And just to make it a little bit more general, now the idea is that we think of weights. The usual idea of weights is that we know it's a force that pulls us down, but we also associate the idea of weights with standing on the ground, on Earth. Right? If you are in outer space and there is an attraction from another planet or another star, we would just think of it as some force. So to make it a little bit more general, I can also write the formula as F over m, force divided by mass, where we would now understand the force here to be the force from this field. So in this example, the force here would be a gravitational force. So it can be from another mass. It doesn't have to be from the ground. It can be from the moon, from the sun. So therefore, with this idea, I can now extend this idea of G. I don't have to restrict my idea of G to just the 9.81 meters per second squared when I'm actually standing on the ground. I can extend it to the force or to the field strength when I'm very far away from the ground. When, say, if I take a spaceship and go to the moon or go to a place quite far from Earth. So let's think about that. So let's say this is the Earth. Let's say I take this ball and I bring it many thousands of kilometers away from the Earth. So that's the Earth. My Earth is so my Earth is a big yellow ball, and I bring my little ball, maybe 100,000 kilometers away to some place quite far, maybe quite close to the moon. So when it's that far away, the force from the Earth acting on it would be a lot weaker. I have a much smaller force of gravity now. But I can still think about a G when it's that far away. But the meaning of the G, I have to describe it as the force divided by the mass at this distance, at this position. So the G here would no longer be 9.81. Right? It must have a smaller value because the force must be so much smaller now when that is further away. But I can still call this a field strength. You can still call it field strength. If you like, we can still call it an acceleration due to gravity, but it wouldn't be the familiar 9.81 meters per second squared. But we can still calculate this with a formula, and that formula is the Newton's law of gravitation. Let me write down that law of gravitation here. Newton's law of gravitation says that the gravitational force is equal to big G, that's the gravitational constant, times the two masses, in this case the mass from the Earth, which I call big M, and the mass from the ball, which I call little m, divided by r squared. So if I want to make a formula for the field strength, that is the force per unit mass for an object here at some distance, let's say from the center of the Earth, let's say a distance of r from the center of Earth. So I would just substitute this formula for the force into there, and that's it. So let's do that. So this will be equal to G m over r squared from this formula for this force, and I still have the m at the bottom. So this is it. Okay, and to simplify this, I can cancel the m there and cancel the m there, and then I have G m over r squared. And now we have our formula for the field strength.